we go. Okay, so our final exam is next Wednesday. I don't know if anyone has checked on that, but that is when it is. So we are writing next Wednesday at 1 p.m. I'm just going to confirm that via the old PeopleSoft here. Yes, 1 p.m. Okay, so I'm going to make a note, a random note. So here we are on April 7th, 21. So our final exam is on April 14th. Okay. Okay, and then this is going to be from 1 to 4 p.m. All right. So the final exam is going to be run in the exact same way that we ran the lecture quizzes. So it'll be it'll be completely done through CrowdMark. So the exam window or the test will be sent out at 12:50 p.m. So 10 minutes before the start time, same as it was for the quizzes. And then you will have until 4 p.m. to submit your answers, same as you did for the quizzes. So the full time period. So that's 3 hours, 10 minutes to get all the pictures taken and uploaded. The questions will appear on the CrowdMark page the same way they did for the quizzes. And then, figures and tables will be downloaded from said CrowdMark page the same way it was for the quizzes. Now, that being said, I'll try and make sure all the tables and the figures are labeled appropriately, like question 3, part A, question 4, and that kind of thing, just so they're a bit easier to keep track of. As you might expect, like there will be quite a few figures and tables on this final because of the nature of the material that we're working with. So again, I'll just try and keep that as organized as possible for you, but this is something that you'll have to kind of keep track of yourself too as you're working through the questions. The final exam is a cumulative exam. We still have a little bit of work to cover from this lecture set, but what I'm going to do is basically wherever we finish today is the end of what we're going to cover. Like all of the material that we're into now is really kind of bonus material anyways, because this is stuff that, with the categorical inclusion, like this wasn't material that we had seen on assignment 6. So it's all extra. So we're not going to be losing out on anything if we don't finish lecture set 13. And just in fairness, because the final exam is next Wednesday, it doesn't seem reasonable to continue to do new material into Friday's class and potentially next week. So wherever we get to at the end of today's lecture will be what the final exam covers up to. On Friday, then, we will start review for the final exam, and then we'll continue reviewing for the final exam on Monday, leading into Wednesday's test. So the good news is you'll be done your 252 exam quite early in the period. So then you can move on to focus on other stuff. The bad news is just that it's, a real quick turnaround from Monday to this first final, but it's probably the case that most of you would have at least one exam on the first or second day anyways. So, it's just kind of, it is what it is in terms of the scheduling. So with that being said, we're going to continue to work through lecture set 13. I'm just going to take a peek at what I have lined up here. So we have to do this extra sum of squares F test. And then I have some model selection, material, forward selection, backward elimination, and then kth order regression. So there's 2 topics left to cover in this lecture set. Both of them are interesting, but they're very different topics. So we'll probably just go in order, talk about forward selection. The kth order stuff isn't really that big of a deal. It's pretty case specific, I guess. But this material that we're covering right now, this is actually so if you're in statistics and you're interested in taking more on regression analysis, we offer a third-year class, Stat 378, which is strictly devoted to the study of linear regression models. And in that class, the information that we've covered on categorical inclusion and what we will see snapshots of in terms of forward selection, backward elimination, and then the kth order modeling, that's all covered in that material, in that course as well. So we'll get to kind of what we get to by the end of class today, and then we'll start review on Friday, as I said before, because that just seems like the most fair thing to do. Okay. So we left off last Wednesday, it's been a while, talking about including categorical information within a regression model. So just as a reminder, when we include a categorical variable in our regression model, we basically code the categories as values. So we create what are called dummy variables, and the dummy variable is used to represent the levels of the categorical variable of interest. So in the example that we're looking at, we have one dummy variable, which represents the timing schedule for at which these plants are submitted to light. So our response variable, y, is the number of flowers that have grown on a particular plant. Each of the plants are exposed to a different light intensity. That's what we call capital X1, and we consider this to be a quantitative variable. So this is a variable that we can include in the model naturally. And then we're also considering a timing schedule, where the timing schedule is coded as late versus early. So in order to incorporate this information, we let late be equal to 0, which is the reference level, and we let early be equal to 1, which is the the active level, I guess you can say, of the dummy variable. So we're just taking the categorical information and recoding it as a 0 or a 1. And that's how we include said information. Now, from that, we've effectively been studying the influence that this has on the model. So for example, if we consider the categorical variable in our model, this variable actually only influences the intercept of the multiple linear regression model that we are working with. The reason is the value of x2, which is the categorical variable, can only be 0 or 1. So if x2 is equal to 0, that term cancels out. If x2 is equal to 1, you're just adding the b2 value to b0. So you have a set of what are called parallel lines. And this is what's created whenever you include categorical information within a multiple linear regression model. Now, you can also interact the categorical variable with the explanatory variable. And that's the model that we were considering when we left off last Wednesday. So the MLR model showed on slide 38 here. This is our MLR model where we have an explanatory variable interacting with a categorical variable. Now you can see that what happens here is you have a structure that is similar to the interaction model that we studied earlier in the course. The difference is when you include a categorical variable, the interpretation of the coefficient for the interaction term actually is easier to define and has more meaning. So essentially, when you have a interaction between a continuous variable and a categorical variable, when you shift from the reference level to the active level, so when you let that categorical variable equal 1, the interaction term changes or represents the difference in the slopes between the reference level model and the active level model. So it's similar to how the categorical term influences the intercept, except that this interaction of the continuous and categorical variable plays a direct role on the slope of the other quantitative variable in the model. Okay, so we can effectively interpret this value directly based off of the coefficient in the model. Whereas when we have an interaction between two quantitative variables, we don't have that ability. The reason is because you have so much effective, like because the range in which a quantitative variable can take on is so wide, every time you change a value, the interaction term plays a different role on the slope of the free variable. So it's much more, it's more difficult to interpret because it's changing all the time. Right? But that isn't the case when we mix the quantitative variable and the categorical dummy variable together in this style of model. Right, so on slide 39, we talk about these interpretations. And again, the big thing to take away here is that when we include the categorical variable, we have the ability to directly interpret the slope or the coefficient that is attached to the interaction term. And we don't have that same ability when we consider an interaction model that interacts two quantitative variables. Okay, so on, we left off looking at an extra sum of squares f-test to compare the full model with interaction to the reduced model without interaction. Now, what I want to show you here is the relationship between a t-value and an f-value when your reduced and full model differ by only one term. Okay, so in this question, the only information that we have is the standard error of B3. Okay, so we're told that the standard error of B3 is 0.010515. We do know that B3 itself is equal to 0.001210, and that's given to us on slide 38, right? So this is B3 right here. All right. So we want to compare the reduced model and the full model, and we want to know, like, do we actually need the interaction term? Based off of the diagrams that we have constructed, we don't believe there is an interaction. So the lines that result when you have late light versus early light from the MLR model that we are considering are effectively parallel to one another. So that would imply that we don't need the interaction term. But we want to test this to determine if there's statistical evidence from the data that this interaction term is not needed. So to do that, we can perform an extra sum of squares f-test. Now, in this particular example, we don't have the sum of square reduced or the sum of square full given to us. Okay, what do we do in this case? Well, what we can show is that these two models differ by only one term. Okay, so that means that this test statistic here is going to be distributed on F 0.051 and then the DFE for the full. Okay. So since models differ by one term. Okay. Okay, so the fact that the first degree of freedom is a 1 means that this f value is actually the square of the corresponding t value on the same degree of freedom error. Okay, so note, I'll write that down here. When df1 is equal to 1, f alpha 1 dfe is equal to a t square on alpha dfe. Just want to make sure it's not, it might be alpha over 2. I'll just check this real quick. sense. There you go. So this would be equal to this, and it's on alpha over 2, the two-sided test, which makes more sense anyways. All right. Okay, so why is this helpful to us? Well, if the F test statistic on step 3 here is following an F distribution where the first degree of freedom is a 1, that means that we can actually get this F value from the T value directly. The other thing that this means is that a test about B3 using the T value will give the exact same solution as the extra sum of squares F test. All right, so in general, an extra sum of squares F test where the reduced and full model differ by only one term is identical to the T test about that individual term. All right, so from this, we can say, therefore, capital F is equal to little t squared, which is equal to B3 minus 0 divided by the standard error of B3. Okay. This is equal to 0.001210 minus 0 divided by 0.010515 squared. Which is equal to 0.0132. Right? Okay, and the note here so this is the test statistic for H0 beta 3 equals 0 versus HA beta 3 is not equal to 0. Right, so the takeaway from this is we can test for basically the inclusion of the interaction term or whether or not the interaction term is needed using either the T test about B3 or the extra sum of squares F test. And we can only do this because those two models differ by one term. On assignment number 6, we hadn't quite gotten to the reason why you can do this yet, but we had the T value information, so we were able to test B3 directly using the T value in question number 6 on that assignment. But this is the reason why you're allowed to do that. Okay, so the T test and the F test, when the first degree of freedom is equal to 1, are going to give the exact same solution. Right, so we can see here that our F test statistic is therefore 0.0132, which is basically 0. So it follows that on step 4, like say we took the critical value approach. So if we had an F 0.051 comma DFE full, I guess we got to work this thing out. So DFE full is going to be, how many observations do we have? 1, 2, there's a better table here. Here we go. 2 times 1, 2, 3, 4, 5, 6, 12, 2 times 12, 24 observations. Okay, so we have n times p minus n minus k minus 1, so 24 minus 3 minus 1. Okay, so we have an F value on 24 minus 3 minus 1, which is an F on 0.05, comma 1, comma 20, comma 20. Okay, so this is going to be equal to, so we go to our F table now, 1 and 20. Okay, so that's 4.35. right? And it's real, it should be very obvious that the p-value is going to be greater than 0.1 because it's so small. Okay, now let's look at something else. So suppose that we consider the t-value, right? Okay. Okay, here, I'll just finish this off, right? So then we can, on step 5, we do not reject H0. And then on step 6, we can say at the 5% significance level, the data do not provide sufficient evidence to suggest that the reduced model is not adequate. Okay. All right. Now, like the part that's actually like really cool to me. So consider H0 beta 3 equals 0 versus HA beta 3 different from 0. Okay, so this will be step 1. Okay, so in step 2, we have alpha equals 0.05. On step 3, we have t equals 0.001210 divided by 0.010515, right? So this is going to be 0.1150. Okay, now check this out. So on step 4, we're going to do the critical value, right? So here's our critical value, 0.025, and this is also going to be on 20, which is the DFE. Okay. So this value, if we go to our t table, right? So that's going to be 0.025, 20, 2.086, right? Note 2.086 squared is equal to 4.35. Right? So you can see, like I was saying before, because the two models only differ in that one term, the t-test about beta 3 and the extra sum of squares f-test are actually the exact same test. So one of the ways that you can show that this is true is you can actually see that the critical values follow that relationship that I gave before, which is that the f value is the t value squared when the first degree of freedom is equal to 1. And the critical values from the two tests show that same relationship. So you can see here that the t value on 20 degree of freedom is the square root of the f value on 1 and 20 degrees of freedom, right? So it also follows that, and this isn't as convincing as the critical value argument, but you can see that the p values are also greater than 0.1. And in fact, if we use software to show this, so if you take 0.0132 and you go 120, right, and then you go PT, you can actually show that those two p values are equivalent as well. So like here, for example, you can say from software, the p value is equal to 0.910. And here you can show from software, the p-value is also the same thing, right? And then I actually just check this using R. So it's true. So then you can see that we do not reject. And then of course, step 6 is going to be identical as well. So we have the same conclusion from both tests, right? So as I said, this is a lot of extra stuff, but this particular relationship, so the relationship between the t-test about the interaction term and the extra sum of square test, when the full model only includes that additional interaction term, are the exact same test. And the results of those being the exact same test means that we can actually find the f value or the t value from one another. So in this illustration, just like on assignment number 6, you are asked to compare these two models. But because these two models only differ by one term, you have two ways that you can compare them. You can do this extra sum of squares f test, which allows you to compare some full model to any subset model, or you can do a t-test about the additional term directly. And those two tests are actually the exact same test and will give the same conclusion. And from that, we can actually show that those tests being equivalent means that there's a relationship between the critical values, the p-value, and the test statistics. So we can work out an f test statistic from a t-value anytime the first degree of freedom is equal to 1, which is what I've done here. Okay. Further, you actually don't even need to do the f test if you have the information for the t test, because again, they give the same result. So below, under the red line, I'm just giving the first 5 steps of the t test, but you can see that this is the exact same conclusion as the f test. And in fact, you can see again that relationship between the f value and the t value through the critical value. And you can see that the p values for both tests are equivalent as well, which is what you would expect because again, it's the exact same test. So on assignment number 6, in question 6, when you are asked to test if the interaction term is needed, we only had the information for the t-test, but that's perfectly fine. So you can just do the test about beta 3. And this is the reason why it's okay to do that instead of the extra sum of squares f test. All right. Does anyone have any questions about that? Okay, so there's 2 topics left in lecture set number 13, model selection and fitting higher order regression models. I don't think we're gonna have time to do both, given that we only have 20 minutes left and I wanna start the review class on Friday. I think I'll do model selection because I'm confident we can get forward selection done today, and at least you have that whole concept sort of given to you rather than trying to like sort of parse together the higher order stuff. All right, so why do we need to consider model selection, or what is model selection in the context of a regression model? In this unit, what we have learned is that regression models can include effectively any number of explanatory variables. So we can link our response variable y to x1 through xk, where k could be as high as say 10. Now, the drawback is every time you add an explanatory variable into the model, you make interpretation of the parameters a little bit more confusing, or a little bit, they have a little less meaning, if you will. It's one thing for me to say to you, if the wind speed outside is constant, my car is going to burn 8 liters of gas for every kilometer that I travel. That makes sense to you. But if I was to then say, in a similar situation, like if wind speed outside is the same, temperature outside is the same, tire pressure in all four tires is consistent, you're driving on strictly asphalt roads, and I don't know, you don't have a windshield and you have the sunroof down, then I'm going to burn 8.6 kilometers of gas. Like, even though this has meaning, it's a little bit more convoluted than the original expression. So model selection is effectively referring to the practice of trying to find the most important explanatory variables among a set of variables that are presented to you. So it might be the case that you can include all of these different explanatory variables in the model, but the question is, should you? Now, to answer that question, we develop model selection approaches. There are three main ways of picking explanatory variables in a model: forward selection, backward elimination, and what's called stepwise regression. In this class, we're only going to focus on forward selection and backward elimination. Stepwise regression is actually an amalgamation of those two things. So if you understand how forward selection works and how backward elimination works, putting stepwise regression together is not overly difficult, because it basically just does two forwards and then one back. Okay. Both approaches, the forward selection approach and the backward elimination approach, they can be done in a number of different ways. There's no exact method for performing the approaches. They really just refer to two processes, but the decisions that you make on each step of the process can vary depending on, just how strict you want to be, or which type of hypothesis testing procedure, I guess, you prefer in some sense. We're going to use t-tests because it's the most direct way, and it gives in my opinion, it kind of paints the best picture of how the approach works. Okay, so our data set is shown below. So in this data set, we have 88 observations, and we have 1, 2, 3, 4, 5, 6, 7, 8 different variables. We want to construct a regression model to predict sale price. So capital Y is going to represent the price of the what looks like a house. And then we have a set from X1 to X6 or X7, different explanatory variables that could be included in the model. Okay, so we have our response, which is price, and then we have from 1 to 7 different explanatory variables that we can consider in our regression model. The goal is to only select the explanatory variables that are truly meaningful. So we don't want to include any additional information that isn't going to contribute to the prediction process. Or we don't want to overcomplicate the model if we don't have to, is a better way of saying that. All right, so forward selection is a process that adds one explanatory variable into the model framework at a time. So forward selection begins by assuming that the response variable is a function of only one of the explanatory variables in the model. Okay. Now, the way that this works is we would construct the model utility test of beta 1 equals 0 versus the alternative that beta 1 is different from 0. And we would consider each individual explanatory variable separately. Okay. In the table shown here, we have the t-values for the model utility test, where sale price is a function of each of these different explanatory values, right? So for example, this t-value here is when size is included in the model. Okay, so this represents, we'll just write it as price equals beta 0 plus beta 1 times size. Whereas this here represents price equals beta 0 plus beta 1 times bath. Okay, and then this one here would be price equals beta 0 plus beta 1 times roof. So we consider SLR models for each individual explanatory value. You compute the t-value for each of the models. And then what you do is you say whichever variable is most significant, so basically whichever one gives the highest t-value is the variable you would include in the model. Now, with t-tests, you can reject in both the lower tail or the upper tail. So it doesn't matter if the value is positive or negative. So we're looking at absolute magnitude. So you can see here that age is has the largest absolute t-value. So that implies that age is the most important predictor for price of a sale home. So we would allow age to then enter into the model. So we would say that after step 1 of the forward selection process, we have price is equal to beta 0 plus beta 1 times age. And the fitted model has the form shown on the bottom of the slide. So y hat I equals 290,605.6 minus 8,927.4 times x1i, which represents the age of the house. Right. Does that make sense? Does anyone have any questions about that? It all builds on this. So if the first step is a little bit fuzzy, the second step will not be any clearer necessarily. So any clarification questions? Okay. So on step 2, you now take the model you built on step 1 and you consider every single remaining explanatory variable separately, right? So we now have price, age, and then here it could be any of remaining. So what we do now is we take each of the remaining explanatory values and we consider what would be 6 different regression models where the first explanatory variable is age and the second explanatory variable is one of those 6 possible variables, right? So for example, here we would have price is equal to beta 0 plus beta 1 age plus beta 2 pool. Here we would have price is equal to beta 0 plus beta 1 age plus beta 2 stories, okay? And then here we would have price is equal to beta 0 plus beta 1 age plus beta 2 area. Okay. So we're considering all possible regression models with 2 explanatory variables separate. But the only condition is that the first explanatory variable has to be age because it was the value that entered the model on step 1. Now, once you've done this, everything follows exactly in the same way. So you can see that size contributes the largest absolute t-value. This t-value would be significant at the 5% significance level. So we let size enter into the model, and now we have the regression model shown at the end of slide 47. Okay. Now what we do is we progress in the same steps. So on step 3 of the forward selection process, we would consider all 3 component regression models where age and size have to be included in the model. So we have price is equal to beta 0 plus beta 1 age plus beta 2 size. And then we consider the 5 remaining variables separately. Okay. So for example, here we have price equals beta 0 plus beta 1 age plus beta 2 size plus beta 3 area. Okay. And here we have price equals beta 0 plus beta 1 age plus beta 2 size plus beta 3 roof. Right? Now we consider all of the t-values. The largest absolute t-value is 1.624, but the p-value that corresponds to this t-value is not greater or is greater than 0.05. So that would not be a significant, or that would mean that we do not reject H0. So in that case, we don't allow the variable to enter the model. And then we stop at the last model from step 2, which is the model with 2 components included, the age and the size. So this would be termination of the forward selection process. Any questions about that? Okay, let's talk about backward elimination then, because it's just the opposite of forward selection, and we should have enough time just to go over the idea. So forward selection begins by saying y equals beta 0 plus any one of the available explanatory values. Backward elimination begins by saying consider the full model. So y is a function of all of the different variables within the model. And then it says remove the variable with the smallest absolute t-value, giving no evidence against h0. So literally we're just moving in the opposite direction. So our full model here is going to be y, well, it's going to be price is equal to beta 0 plus beta 1 size plus beta 2 pool plus beta 3 area plus beta 4 age plus beta 5 bath plus beta 6 stories plus beta 7 roof, right? Now we compute the t-values for each of those individual predictors in the model, and we notice that bath has the smallest absolute t-value. This t-value would give no evidence to reject h0, so we can remove this value from the model. So now we have on step 2 the full model that does not include bath. And then we do the exact same thing. So here you can see that pool has the smallest absolute t-value. Okay, so this gives no evidence to reject H0. So we take pool out. And then on step 3, we have stories. Okay, so no evidence to reject H0. So we take stories out. And then we have area. Again, no evidence to reject H0. So we take area out. And then we have roof. And you can see here we have no evidence to reject H0. So we take roof out. And then we have size. But this t-value is very large. So this would give evidence to reject H0, beta 1 equals 0. Therefore, the process terminates, and we'll end up with the same model that we found from forward selection. Okay. Any questions about that? So forward selection, backward elimination are the same goal. They're methods for determining which value should be included in our model. The difference is forward selection starts from the null model that has no explanatory values included in it, and then it builds the model up. Backward elimination starts from the full model and then drops values out until no value should be removed. Any questions? Okay. All right, so I'll stop there then, because I won't be able to do kth order regression in 5 minutes. But as I said, so this is where we'll finish off for this semester. Okay, so conclusion. And then on Friday's class, we'll start review, and I'll start getting practice problems and some sample stuff up for you today so that you can start prepping for the final, which again is next Wednesday. And as always, if you guys have any questions, please let me know. We have our lab exams on Friday, so that's the only remaining assessment before the final exam. So those will be held in the 8 a.m. lab and then at the 2 p.m. lab with whoever your instructor is. Yeah, and outside of that, as I said, we'll just start review on Friday. We'll continue with review on Monday, and then we'll have the final exam on Wednesday, and then we'll be done with 252 before we know it. And we'll be on to our next semesters at McEwen. So if you guys have any questions, let me know. Otherwise, I'll talk to you on Friday afternoon. Oh, and sorry, one more thing. If you get a chance, can you please fill out the course evals? I would really appreciate it. It's hard to get higher response rates. So if you guys can find some time, good, bad, or ugly, doesn't matter. Just, your honest opinions to help us develop going forward and all that good stuff. So if you can find some time to do that, that'd be great. And otherwise, I'll talk to you guys on Friday afternoon.